everybody. This video is going to be about calorimetry. Calorimetry is going to be an extension of our specific heat problems. We are still going to use Q equals MCAT. The only difference here is that we are going to be trying to solve for information regarding a substance that we don't quite have enough information on. And so in order to solve the problem, we're going to see how it interacts with another substance. So what we're going to be doing is taking things like hot pieces of metal and putting them into cold water. And we can easily measure how much the temperature of the water changes. And so we'll be able to use the first law of thermodynamics to substitute in some of the information about the water in place of the metal object where we aren't able to get the values that we need. So we're kind of solving a specific heat problem in a very roundabout way, and we're exploiting this law of thermodynamics that says that we can't create or destroy energy. Whatever one object lets go of, one is going to absorb. So that's kind of the concept here. So let's look at some calorimeter pictures. A calorimeter is the device that we use. You can have really fancy ones called bomb calorimeters. They plug into the computer and they're made of fancy material. Or what we do is we can just use coffee cups. We use the styrofoam coffee cups. They're getting a little bit harder to find these days actually, because the styrofoam is a very good insulator. It's not great for the environment, but it does hold the heat in very nicely, so we don't lose energy to the air in the classroom. So all the energy that's being transferred will stay nicely inside the coffee cups. And so we have our liquid in there. We use water typically. We would put our object in. We'd be able to measure the temperature change of the water. Usually we try to stir it somehow so you don't get hot spots and cold spots of the water. You kind of swirl it, keep the water mixed nicely. And we can actually get very, very good numbers with just a couple of coffee cups and a lid. So that's pretty cool. So a common type of question you might see is that we're going to have a hot object and we put it into the cold liquid. That's probably the most common. We could, however, put a cold object into hot water. That's another option, kind of going the other direction. Or we could take 2 cups of water at different temperatures and figure out what they might be once they're mixed together. Or you could do the heat that's either absorbed or released during a chemical reaction. And so these are all varieties of problems you might see, but they're all going to be solved in almost exactly the same way. They're all going to use the same technique of calorimetry to help us solve these problems. Like I said earlier, we're still using Q equals MCAT. We are still doing problems that involve energy being transferred. So one object lets go of the energy, the other will absorb it. So the difference here is that we have 2 substances. So we're going to need to do a Q equals MCAT for each substance. So we will actually have 2 sets of equations. We're going to have 2 sets of masses, 2 sets of Q values, 2 sets of temperature changes, 2 specific heats. We're kind of doubling everything. Okay? So when you read the problems though, it's going to feel like you don't have enough numbers. We are not going to have all the pieces of information that we need. And so what we're going to do is we're going to realize, well, wait a minute. The first law of thermodynamics is going to help us here. We are going to realize that because energy cannot be created or destroyed, the only thing we're doing in these problems is transferring the energy. We are moving it from one object to the other. So, whatever the energy into one object is the same energy that the other gave out. So, energy absorbed, Energy released is another way of saying it. If one object absorbed 20 joules, that meant the other object had to release 20 joules, right? We're not making new energy here. We're not losing it. We're just moving it from one object to the other. So what we're going to be able to do is, instead of saying energy in or energy absorbed, let's just use our Q value, right? Q is what we use to represent the energy. So we're going to have the Q of one substance equaling the opposite algebraic sign for the other. So we say Q equals negative Q. And that sounds a little strange, but remember that a negative sign can just mean opposite, okay? So what we're saying is that one substance will have the opposite algebraic sign of the other. If one is 20 joules, the other is negative 20 joules. If one is 50 joules, the other is negative 50 joules. It doesn't really matter which side you put your negative on. It's not going to matter which side was actually absorbed or released. All of the algebra will work out in the end. So as long as you think of it as like the opposite sign, I think it will help. Basically, we're saying that the energy is equal and opposite. Energy absorbed, energy released. Okay. So let's just do a kind of a quick example. If we have a hot piece of metal and we put it into a cold cup of water, the water absorbs 50 joules, which means the metal had to release the 50 joules. So if I want to set this up with actual numbers, our water absorbed, our metal released. Remember that if it's absorbed, Q is a positive value, so it'll be positive 50. And then the exothermic one will be negative. It'll be negative 50. And then people say, wait, 50 does not equal negative 50. What are you saying? And that's because they're forgetting that we've added in this extra negative sign. So the energy of the water is equal, but the opposite sign of the metal. So look what happens. We get these double negatives, don't we? So 50 equals 50, right? So it all works out by substituting in that extra opposite sign, okay? If I had flipped this and had put the metal on this side and the water on that side, it wouldn't matter. The negatives would work themselves out, okay? So let's just take a minute and remind ourselves. This is not new, but let's remind ourselves of where these negative signs are going to pop up, okay? Mass will always be positive. You're never going to have to worry about that. Your specific heat, always a positive value. You can't absorb a negative amount of energy, right? It's always positive. Therefore, your delta T can either be plus or minus. And that's where your Q value ends up plus or minus. So when you're looking at T values and you're looking at Q values, be careful. Stop and think about the story of the problem and make sure you don't have your algebraic signs backwards or missing. Sometimes people find it helpful to do a very similar thought process of what's plus, what's minus by looking at a little picture, okay? Our energy in will be our energy out. Energy absorbed will be a positive sign. Energy released will be a negative sign. So if I have a beaker with hot water and I put my metal in there, the metal is going to heat up. The energy is going to be transferred into the metal. So compare that to over here, we have our calorimeter. Now let's take this hot piece of metal and stick it in the cold water. Well, now our cold water is going to heat up, and the energy will be transferred into the water. So if we heat up a piece of metal over here in some hot water in a beaker, the metal will be positive in this case because the metal is absorbing, right? The water is releasing its energy, so it'll be negative. Over here in our calorimeter, now the metal is hot and it's cooling down and the water is getting warmer. So the metal will be negative, the water will be positive. So depending on the little story of the problem, you may end up with different algebraic signs. Now, if I leave this piece of metal in my calorimeter long enough, the metal cools down, the water heats up, and eventually, if I wait long enough, the final temperature of the water is going to equal the final temperature of the metal. We say they equilibrate. They come to the same place. That is going to be incredibly helpful to us. I cannot easily stick a thermometer inside my solid chunk of metal, can I? I can't like shove that thermometer down inside there. And so what we do instead is we measure the ending temperature of the water. And that will tell me what the metal temperature was. If you don't wait long enough, this doesn't work, okay? You have to be patient. You have to wait long enough. You got to wait for the water to stop changing temperatures. These labs sometimes take a long time because so many things are heating up and cooling down, and you have to be patient. But if you're patient, you can realize that, well, if I can't measure my metal, I can indirectly figure it out by measuring the temp of that water, okay? So, let me kind of show you some things that you would use in a calorimetry experiment where you would be finding your numbers, okay? So for this experiment, we heated a piece of metal up in some boiling water, and we let it sit in the boiling water for a long, long time until that piece of metal was really, really hot. Then we take the hot metal and we stick it in the calorimeter with the cold water, and we're going to have that temperature be change in the cup of water, right? So over here, we don't know what the energy transfer of the water is, right? I don't have a device that I can stick in there and it tells me like a thermometer, right? I don't have a device for that. So that's what we're going to have to try to solve for. I do know the mass of water. However much water I pour in my calorimeter is the mass of water, right? If I pour in 50 milliliters, that's 50 grams. If I pour in 100 milliliters, that's 100 grams. I do know the specific heat of water, 4.184, something to memorize, right? Usually, we're fine if you do 4.18. You're not going to get off that much if you don't use that last decimal, so no big deal. Now, the delta T of the water is very easy to find in a lab. All you do is you use your thermometer. You measure the temperature before you start. You measure your temperature when you're done. Super easy, coming straight from your thermometer. The values for the metal can be a little bit more tricky. Realize that the Q of metal will be the opposite of whatever the water was. Remember, because energy in equals energy out. If you want to be generic, remember it's an opposite sign. That way it won't matter if you're doing a lab where you heat something up or cool something down, right? If you think of it as opposite, it'll be a little bit easier, more generic. The mass of the metal is easy to get. You just put it on your scale. but we don't know what our specific heat of metal is, right? These labs are where we're trying to find these specific heat values. We don't know what metal it is. We want to try to figure out what the specific heat is. So we don't know that number. The temperature of the metal, the delta T for the metal, can be a bit tricky. We know that it's going to be T final minus T initial. But what's T final? And what's T initial? So realize your final temperature will be the same as your water's final temp because we're going to be patient and we're going to let them equilibrate. So they will end at the same temperature. Now, because for this lab we put the metal into boiling water, we know what temperature water boils at, don't we? Water boils at 100. And if I leave that metal cube in the water boiling long enough, eventually the entire metal cube will get to 100 degrees. So my final temperature is from the water, and my initial temperature is actually 100 because I was boiling that cube in water. I think it's incredibly helpful for you to copy this down with all the little notes about where you find your numbers, because when we do get to the point of doing our lab, people sometimes will get overwhelmed and forget where their numbers are coming from, okay? So take a moment, make sure you have these down. All right, let's do a couple practice problems. You have a glue-in that has the actual questions. So it would be helpful for you to put that in your notebook. Remember, since I've been telling you since the first day of school, you got to show your work the way I do. One of the things that we're supposed to assess you on is, can you adequately convey your thoughts and your process and the scientific concepts through clear math, right? Through clear work. Conveying scientific ideas in a clear way. One thing I'm going to encourage you to do that you'll see me do in the practice problems is annotate them, right? So highlight them, little notes off to the side, little reminders. Okay, remember that we're taking notes. We're not just doing a worksheet as fast as we can, okay? So please use that skill of annotating, okay? All right, so first practice problem. Calculate the specific heat of a metal if 2.36 times 10 to the 2 grams of it are at 99.5 degrees added to 125 mils of water at 22 degrees. The final temperature of the system is 25.4 degrees. People will have one or two reactions. They either freak out and go, oh my God, it's so many numbers, I don't know, right? Or they'll have the opposite and they'll say, there's not enough numbers, I'm missing numbers, I don't know what to do. So what I think can be helpful is to color code them. You're going to have one color for the metal, one color for the water, and what I personally like to do is pick colors like yellow and blue so that when I'm finding numbers that work for both materials, they combine and become green. So if we were in class and we were, all together, I have a big bucket of highlighters and I would pass out a yellow and a blue one to everybody, okay? I'm not saying you have to use those colors, if you're watching the video, but it is something that might be helpful to you. So let's read through this and let's try to find all of our values and let's try to color code them as well. So calculate the specific heat of a metal. That's what I'm solving for. I'm going to underline the thing I'm looking for. And it's for the metal, so I'm going to color code that yellow. I have 2.36 times 10 to the 2 grams of that metal. And it's at 99.5. So I have a bunch of values for this piece of metal. I'm going to add that hot piece of metal into 125 mils of water The water's at 22 degrees. So now I have some values for the water inside the calorimeter. When I'm all finished, the final temperature of the whole thing is 25.4. That's going to tell me the temperature of not just the metal, but also the water. So you can see why I picked those colors, right? Now green is the one that goes with both. Okay. So I am going to highly encourage you, after all these years, seeing who tends to do well and who tends to struggle, who tends to get lost in all the numbers and have a hard time finding their mistakes, I've noticed if you make 2 lists of your values before you start the problem and you label which is which, you're going to do a lot better, much safer. Okay? So we're going to have Q equals MCAT values for the metal, and we're going to have Q equals MCAT values for the water. I don't care if you put the water first and then the metal. Remember, it doesn't matter. We'll just be opposites. Now, because we're going to be setting some equations equal to each other, right? Energy in is opposite of energy out. We don't actually need the Q values, okay? We're not going to need those numbers. So let's put in the numbers we have. We have the mass, but we don't know our specific heat. We do, however, know the specific heat of the water because I've memorized it, right? Right, just something you should know. We had the mass. Now let's look at the delta T's because they're a little bit more complicated. It's going to be T final minus T initial. I also suggest putting some kind of a note about if it's heating up or cooling down. That's going to make sure that you don't get your positives and negatives messed up if you kind of make a little note to yourself. So we know that in the story of this problem, the metal is cooling down. Over here, we'll put our actual values. We ended at 25.4 minus what we started at. And you can see we get a negative delta, which makes sense because we cooled down. Over here, it's still T final minus T initial, but the water should be heating up. We end at 25.4, and we started, the water was at 22. So the water will heat up 3.4. People get really upset about this, okay? They really don't like that the metal is going to change by 74 degrees and the water is only going to change by 3 degrees. But you have to think about the fact that the water can absorb a lot of energy before those molecules start moving faster due to all the chemical nature of water. And so because it can absorb and absorb and absorb and absorb more and more and more energy before the temperature goes up, you will see a smaller delta of T for the water than you will the metal. 4.18 joules per gram is a lot of energy, right? So that's why we don't have a big change in our Celsius, in our delta T. That's one of the reasons why it's so important that we have water on the earth, because the water can absorb a lot of that energy, right? Without huge fluctuations in temperatures. Okay. So now we know that the energy of one of the objects is the opposite of the other. We also know that Q equals MCAT. But I don't have these Q values. I have no device that measures this, okay? So I'm going to substitute. I'm going to take the MCAT portion and I'm going to plug it into my Q's. I'm not going to say Q equals negative Q anymore. I'm going to say MCAT equals negative MCAT. And now if you look, we have lots of numbers we can plug into this version of the equation, okay? Once again, it does not matter which thing is substance 1 and which is substance 2. That little minus sign will make everything work out just fine, okay? So, right, does not matter. If you want to switch them, switch them. I don't care. I will never mark you wrong if you have substance 1 and substance 2 backwards from me, because you'll get the same answer, okay? So, we have the mass of metal. We don't know C, and we can plug in delta T. So we have our mass times the variable that we're looking for times my delta T, which is negative because it was cooling down. That's going to equal the negative sign, right? Can't forget that negative. Mass of water, specific heat of water, delta T of water. Now what do? Now you just isolate your variable. You just do a bunch of algebra, okay? See if you can figure out what C is. What is the specific heat of that unknown metal substance? Were you careful about those negatives? Do you see how those are going to cancel each other out? That's why it doesn't really matter which side you put things on. They'll get sorted out. You're looking for that thing, right? You're looking for the C value. Punch it in your calculator. You should end up with the specific heat of this unknown metal is 0.102 joules per gram degree Celsius. It only takes 0.102 joules of energy to get a gram of that material to have a temperature increase of 1 degree Celsius. Compare that to water. It would take 4 joules to get a gram of water to go up by 1 degree. It takes way more energy to heat that water up. Sometimes you may calculate your C value, and then I may ask you to go look at a table of specific heats and figure out what metal it was. That's what you'll do in your lab. You'll calculate a specific heat, you'll compare it to some known values, and you'll be able to figure out what that unknown metal was. All right, let's do another one. A lump of chromium has a mass of 95.3 grams and a temperature of 90.5 Celsius. It's placed into a calorimeter with 75.2 milliliters of water at 20.5 degrees Celsius. After stirring, the final temperature of the water, the chromium metal, and the calorimeter is 28.6 degrees. What was the specific heat of the chromium? Do not just go look it up in a chart, okay? If I'm asking you to solve for the specific heat of a metal in a practice problem, there is a very good chance that I have made up completely random nonsense numbers to generate a random practice problem. So it may not match the real life number, okay? So let's go through and highlight and color code. I'm going to use yellow for the metal and blue for the water, and I'll use green for values that they share. So the mass of the metal was 95.3 grams. The temperature was 90.5. Our calorimeter had 75.2 mils of water. Our temperature is 20.5 for that water when we start. After we stir it, we let everything equilibrate. Everything is, coming up to the same temperatures as each other. The final temp of everything together is 28.6. And we're looking for that specific heat of the metal. So what I'd like you to do is you have one list for your metal, one list for your water. Remember, we're going to use this first law of thermodynamics to our advantage. We're going to be able to say that MCAT equals negative MCAT. like you to try to come up with what your values are, and then see if you can plug them in to an MCAT equals negative MCAT setup. All right, so the mass of the chromium was 95.3. We don't know what our C value was. The mass of the metal was of the water was 75.2. I've memorized the specific heat of water. Remember, we don't need to know what the Q's are, just leave them blank. We don't even care. Delta T, final minus initial. The metal cools down. I'm ending at 28.6. I started at 90.5, so the metal's going to cool down by almost 62 degrees, and my minus sign makes sense. Over here, this time the water will be heating up. I'm ending at 28.6. You see they match each other. I started at 20.5, so I heat up by 8.1 degrees. Makes sense, the metal's going to change in temp a lot more than the water does. Please be careful with your negatives. I think that's probably one of the biggest mistakes, and we will sometimes ask you a conceptual question at the end, and if you get your plus and minus wrong, you're going to get that part wrong too, because those plus and minuses really mean something to the story of the problem. It's really telling you the direction, right? Really important. So I'm going to have a chromium MCAT. I'm going to set it equal to a negative MCAT over here for the water. If you flipped it and you put water on one over here and you put the chromium over here, I don't care. MC delta T equals negative opposite MC delta T. Some people will not like that the water is heating up and I put it on the negative side. But I don't care, it's just an opposite sign, okay? Totally doesn't matter. I'm clearly repeating that 5 bazillion times in the lecture, right? But it's still going to be something people ask me over and over. So I'll say it over and over and over. Now, isolate your variable. You're solving for that specific heat. And you find that chromium is 0.432 joules per gram C. You aren't always solving for specific heat. I might give you the specific heat and ask you how much the piece of metal weighed. Or maybe I ask you how many grams of water were in your calorimeter. Okay, I could ask you to solve for different things. I could ask you to solve for the change in temperature. The trickiest thing to solve for, of all things, I think the one that people have the most trouble with is when you're solving for the final temperature. Solving for the final temperature is hard because people make algebra mistakes, okay? So you have to be very methodical, very careful, keep track of double negatives, make sure you're moving things to the right side of the equation, you're combining like terms, all those kinds of things, okay? So let's do a problem where we solve for the final temperature. There is another little twist to this problem. Read the question to yourself and see if you can find the other thing that I did that's a little bit weird. let's go through and try to highlight. Okay, we're talking about the water first. Okay, let's see. I got 100 grams sample of water. It's at 50 degrees. Oh, wait a second. It's mixed with 50 grams of water? I'm mixing 2 waters together? I don't have a metal. I have 2 cups of water. Who cares? It doesn't matter. You still have 2 substances, okay? Instead of putting metal into water, you're putting 1 cup of water, pouring it into another cup of water. It doesn't matter. It is still an MCAT equals negative MCAT problem. It's actually an easier question. Because the specific heat of water will show up on both sides of the equation, you can cancel it out. So you actually end up with a shorter problem. Okay? Don't let it bother you that it's 2 cups of water being poured together. All right, the second sample of water is at 20 degrees. So 1 cup of water is warm and 1 is cold. We have 100 grams in 1 cup. We have 50 in the other cup. And we want to know, what is the final temperature? Do we care about the total mass of the water once it's poured all together? Nope. We don't care. It's just extra info. Okay? Sometimes that happens in these problems. You have to be able to recognize information that's not needed. One of the best ways to do that is to have your list. Because if you have a number that doesn't fit anywhere, there's a good chance it means it's just extra information. So I'm going to label it water number 1 and water number 2. Okay? That's how I like to kind of keep track of it. Well, we have 100 grams of water in 1 cup with a specific heat of 4.18. Over here, we have 50 grams of water with a specific heat of 4.18. Now let's do our delta T's. Final minus initial. Final minus initial. And you should notice this time I don't know what T final is, right? And so I'm going to leave it TF minus 50 or TF minus 20. I'm going to leave it like that, and I'm going to plug that into my equation. So yes, I will have TF on both sides. It doesn't matter because they're the same number. You have to remember that when we are done and these substances have been left long enough, they will equilibrate and end at the same temperature. So the TF is going to be the same number when we're finished, which means we can combine them. If you have X on one, place and 2X somewhere else, can't you combine those together? We're going to do the same thing. 1/2 of my equation will be for water number 1. 1/2 will be for water number 2. I have mass M C delta T equals negative, because it's the opposite, MC delta T. No, it doesn't matter if you put, the water is on opposite sides. Who cares? If it's flipped, it's flipped. It doesn't matter. So, I know you probably feel like I'm a broken record on this, but yet I still have people who I really do think would do better and have an easier time if they actually put more effort into showing step by step the work they're doing. Okay? Everybody wants to just punch it all in their calculator and be done. But I would rather write it on paper and get it right. Okay? So, we'll just keep saying it over and over and hoping people listen. So let me show you solving now for TF. I just have some little tips here. I think people tend to do better if you distribute first and then isolate. Remember, even though it feels more complicated, you're still just doing rearranging. That's all you're doing. Make sure you don't forget to distribute your negative signs, okay? That's another thing to be careful of. So just some little tips off to the side. Now, same setup from the last slide. MCAT equals negative MCAT. But look, I am going to cancel out these specific heats because they match. If they're on the same side, I just get rid of them, okay? Makes it so much easier. Now what I'm going to do is I'm going to distribute. So 100 grams times TF and 100 grams times negative 50. And then on the other side, I'm going to do the same thing. Negative 50 times TF, negative 50 times negative 20. That's where that double negative can be a real problem if you forget. So I end up with 100 TF minus 5,000 equals negative 50 TF plus 1,000 because we had that double negative. You got to get your TFs on the same side. Since this is the negative one, I'm going to try to move it to this side because I don't like negatives. Then I'm going to move the 5,000 over here for the same reason, trying to get things all separated out. Now I have 150 TF equals 6,000. I divide by 150. And I find out that my final temperature of the water, all poured together, all in one cup when it's all finished, will be 40 degrees. I think it's smart to stop and ask yourself if it makes sense. People, especially on TFs, will get a number that makes no sense. You can't pour 2 cups of water together and get a temperature that's hotter than either, right? You're not going to pour 2 cups of water together and end up with a temperature that's lower than either of them. So stop and make sure it makes sense. Is my final temperature somewhere between 50 and 20? Yeah, so I'm probably off to a good start. Next, ask yourself, okay, did I have more of the hot water or more of the cold water? Well, I had more of the hot water, which meant it's going to cool down, but it's not going to cool down super, super far, right? So if you look, my final temperature is closer to the hot water because I had a lot more of it, okay? So you can kind of stop and say, okay, does that even make conceptual sense? Highly, highly suggest you check on a T-final problem, okay? Last slide I want to just show you because inevitably somebody is not going to notice. They're not going to remember that the specific heats cancel on a question like this. And so what I wanted to just show you is if you forgot and you just distributed it all anyways, it doesn't matter, okay? If you just left the specific heats and you did 100 times 4.18 times TF and then 100 times 4.18 times minus 50 and then, right, if you did that everywhere, look what happens. Do you get larger numbers on each side? Yeah. Do you have to do anything different? No. Look, I'm still isolating my variable, moving things around, right? Dividing to get it by itself. And even though I'm working with bigger numbers, look what happens to T-final. I still get 40 degrees, okay? So if you forget, if you don't cancel those specific heats, it won't change your final answer. You just have bigger, more annoying numbers to work with, okay? So I just like showing people that because sometimes they get worried that they won't remember, right? They'll kind of be just on autopilot and they won't cancel them. Doesn't matter. I will not care, okay? I promise. On a quiz, regardless of if you canceled them or you worked it all out while they were still there, I won't care, okay? These do take practice. I think that the lab is going to go much easier if you are very thoughtful on your homework, showing your workout, because you want to get to the point where the math and the algebra is not something you have to think about. When we do a lab problem, knowing where to get your numbers from is where all your thought and energy should go, okay? So keep that in mind when you're doing your homework, is that, be very diligent about that, and the lab will go way easier, okay? All right, everybody, that was a long one, but that is it. I hope that was helpful. Bye.